examples I'm going to go through are all in the notebook already, so you can just follow along on the screen if you can't get it running on your own computer. If you do have it running, then it's in the tutorial contents repository. And if you haven't done a git pull this morning, you should do that if you've got things set up otherwise, because there is some new content this morning. So just go into that repository, CD into there, and do a git pull. And then you should find under tutorial contents that there's a visualization directory. And under that, notebooks. And so there's, I think, 4 different notebooks that we're going to go through today. Tony and I are going to kind of trade off. I'm going to start out with this one titled Crescent City Inundation. And let me just, I'm going to clear all the output just so that we can start from scratch, at least on what I'm doing. So first of all, I'm going to talk mostly in this first section anyway about just using Matplotlib for plotting things, which is a very sort of the basic Python plotting package. How many people have used Matplotlib already and feel comfortable with it? A few. How many people have used MATLAB for plotting but haven't used Matplotlib? More, okay. So if you're coming from MATLAB, the nice thing about Matplotlib, as the name sort of suggests, is a lot of the syntax is based directly on the MATLAB plotting syntax. So if you're familiar with MATLAB plotting, a lot of what you can do in Matplotlib will feel pretty comfortable to you. You can also do a lot more fancy things and more object-oriented type of plotting, but you can do a lot of things, especially in the notebook or at a IPython shell, using exactly the same sort of commands you're used to in MATLAB. And if you're not aware of this web page, it's one I found very handy when I was first learning Python coming from MATLAB. It's called NumPy for MATLAB users, and it gives kind of a long list of equivalent commands between MATLAB and NumPy, for example. So if you're familiar with doing things in MATLAB and you're having a hard time figuring out how do I do the same sorts of things in NumPy with arrays, that's a really useful site to look at. So if you just Google NumPy for MATLAB users, you'll find that. And if you have questions as we go along, by all means, interrupt me. So I'm going to go through this kind of quickly because we've got a lot of material to cover and only a little over an hour to cover it. But a lot of examples in the notebook you can go through more at your leisure and see how different things are done. Another good resource is this Matplotlib gallery, which is linked at the top here, which has a lot of sort of figures, and if you click on the figure, you see the code that produced it. So if you're trying to figure out how do I do a certain thing in Matplotlib, that's a really good site to look at. Okay, let's see if I can get a little more real estate here. Okay, that's maybe a little better. So I'm going to use a sample data set that comes from some of the work that I work on here in the Pacific Northwest. We're worried a lot about tsunamis coming from subduction zone earthquakes. We have the Cascadia subduction zone that runs off the coast here. So I work mostly on numerical methods for solving differential equations, but over the last 10 or 15 years, we've focused a lot on modeling tsunamis using shallow water equations to model the propagation across the ocean and inundation on shore. So I'm not going to talk about that at all, except to say that's sort of how this data that we're going to look at was generated. And so this is simulation data coming out of a computer model rather than observational data. But a lot of the same techniques you could apply to lots of other sorts of data sets. So in particular, we're going to look at some data that came from modeling Crescent City, California, which is a small community up near the Oregon border. And because of its location, it's sort of just onshore in a interesting sort of topography, and there's also an offshore ridge that kind of acts as a waveguide. It tends to get hit very hard by tsunamis. So anytime there's a tsunami in the Pacific, there's usually an effect in Crescent City. So this is an aerial view of the city, and you can see the shoreline here there's a park which used to be part of downtown until the 1964 earthquake, when several blocks of downtown were destroyed by a tsunami, and so they rebuilt with a park on the waterfront. And there's a small boat basin over here that was heavily damaged in the 2011 Japan tsunami, for example. So there's a lot of concern about what would happen to communities like this in a future Cascadia earthquake, which could be much larger. So anyway, that's sort of the setting for this. So to get started here, I use this Matplotlib inline command, which just says that when I make a Matplotlib plot, it should show up in the notebook rather than opening up a separate window. You can also, if we have time, we'll demonstrate if you do Matplotlib notebook instead of inline, then the plots are actually interactive, and you can zoom in on them inside the notebook as well. But Matplotlib inline just produces a sort of static plot within the notebook. And then I import a couple of things, NumPy, the array package, as NP, and matplotlib.pyplot as PLT. Those are sort of the standard abbreviations that people often use for those. This next line just makes the notebook work in either Python 2 or 3. So we always use print as a function rather than a statement. And then in the next line, I'm importing a function read ASCII file from a data tools module, which is just a file that I created that's in this directory. If you click on this link, you can see what that looks like. This is just a file that reads in a data file that's in a particular format, this ASCII raster format. There are, of course, many other tools like Rasterio that you've heard about for reading in files like this, but I put this in just in case you want to see how in Python would I parse some file format and read in a file if you happen to encounter some other format. So we're just using this to read in some data. So within this repository, there's also a GeoClaw output directory, which has some data, which this hmax_cc.asc is an ASCII raster file that has maximum flooding depth over the community of Crescent City from some hypothetical earthquake. And so I read this in. This file is a format that has a header and followed by lines of data. And so this little routine simply reads it in. When I set verbose equal to true, it prints out what the header is. So we see this is a fairly small 146 by 128 array of grid points in latitude, longitude. So it's on a rectangular grid in latitude, longitude. And then I'm just sort of unpacking that to get the hmax values, the maximum depth, and the x and y arrays out of it. And then do something similar to read in a file of topography data for the same region. And then the simplest thing we might want to do is just plot the contours of topography. So this next cell produces a contour plot. And so I've defined some contour levels using this arange function to just set up a set of an array of values at 2-meter increments. And then the contour command simply contour of x comma y comma topo, the array that we want to plot with the same dimensions as the x and y arrays, and a list of topography levels, or contour levels. And then, well, color bar in this case doesn't do anything too exciting, but it plots sort of this color bar here where you can see which color contour line corresponds to which level. So that's sort of the simplest contour plot, but there's a lot of things that aren't very good about this plot in terms of trying to use it for our purposes. Well, let's see, actually the first thing I said was wrong here. It seems to be showing up okay in this particular rendering, but sometimes what you see along one of the axes is not the full longitude, for example, but only an offset from some fixed longitude, and then down in the corner it says what that fixed longitude is, especially if you're zooming in on a very small area. So you can fix that by telling it to set the tick label offset appropriately. Also, the aspect ratio is not quite right, because when this was plotted, it plots it sort of with axes aspect ratio that's chosen based on the figure size, not based on the proper relation between a degree of longitude and a degree of latitude, which is not 1-to-1 because we're up at latitude 41, and so degrees of longitude are closer together than latitude lines. The distance, 1 degree of latitude is always about 111 kilometers, but 1 degree of longitude is that multiplied by the cosine of the latitude. As you go closer to the pole, the longitude lines all go together. So we want to change that if we're going to get a map that really looks like it has the right aspect ratio. Also here, it's chosen its own colors for the contour lines. We might want to set the colors or maybe just have them all be black because we're going to plot some other data on top of it. So the next cell sort of shows how you can fix various things. First of all, you can tell it what size figure to make rather than letting it choose something itself. So if you want it bigger or smaller, you can do that. And then this colors equals k in the contour command says all of the colors of all the contour lines should be black. You can give it a list of colors for different contour lines if you want, but k is just the string symbol for black as it is in MATLAB. You can also give RGB strings or various other ways of specifying colors. This next line sets the aspect ratio, and again it's based on the cosine of the latitude, which is about 41.7 degrees, converted into radians. So that sets the aspect ratio properly. And then if you're having problems with the offsets in the tick labels, you can set this use offset equals false in tick label format. And then if the tick labels are coming too close together and get smushed up against each other, it's not really a problem here, but sometimes it is. You can also rotate the tick label axes. So if we do all of those things, then we get something that looks more like the correct dimensions if you've looked at a map of Crescent City and has the tick labels rotated a bit. Questions so far? Okay, so the next thing we might want to do is plot this water depth that we also read in. So these were just the contour lines of topography. So this is the harbor out here, and there's kind of a shallow river valley over here, and then some steeper topography on the other side of town. We'd like to plot this maximum flow depth of the tsunami model on top of that. And so in the next cell, what I've done is, first of all, again, plot the contour lines and make the changes that we made above, but then on top of that, I'm using another function, contour f, which is filled contour lines, to plot the Hmax array, which is the array of flooding depths. And so contour f plots contour lines, but then puts colors in between the contour lines. And again, here I haven't specified exactly what levels I want or what colors I want. So if we do this, what we'll get is some defaults, which doesn't look particularly good, but it at least shows what would come out by default. So here the flooding depth, first of all, 0 is coming out as dark purple. So up here in the hills where there wasn't any flooding at all, we're getting dark purple, and that's probably not what we want. So we'll adjust the colors in a moment. Question?
Yeah, can you describe a little bit about the fig acts and the plot objects and kind of what they each mean and which attributes are associated with which ones?
Right, so as in MATLAB, you can just give the figure command to create a new figure. If you say, if I were running this in an interactive shell, I could also give it a figure number so that I could have several figures open at the same time and be doing different plots on different figures. And figure has a number of other sort of attributes that you can set when you call it, in addition to the figure size. The axes command creates a set of axes within that figure. And the reason I explicitly created that, if you just make a plot, if you don't specify the figure and the axes to begin with and just do a plot command as we did up above, it will create a figure and an axes. Here I wanted to actually get this AX returned so that I could later use it here in setting the aspect ratio for the axes. So the aspect ratio is an attribute of the particular axes within the figure. And so I wanted to get the pointer to the axes so that I could refer to it here. There are other ways to do that. If you just create a figure, there's a GCA command, for example, get current axes, so that the plot that you've just made, you can get a pointer to the axes object itself even after you've made it. But it's easiest to sort of explicitly do it this way. And there are various other ways. In the axes command, you can tell it to a lower left corner and a width and a height, for example, so you can explicitly set several different axes within the same figure, and then get a handle for each one returned so that you can plot one thing in one figure, or one set of axes, another thing in another set of axes, and so on. As in all of Python and using Jupyter Notebooks, if you want to know about something like the axes command, if you just type that command with a question mark at the end and hit Shift-Enter, it gives you the docstring, which usually has some information about all the different keyword arguments that you could specify when you call that, for example.
Thank you.
Yeah. Other questions? Yeah, so this plot has several problems. It's really hard to tell where there's inundation and where there's not inundation. It's hard to tell what was originally the water from the dry land. And so the next cell fixes several of those things. In particular, I'm using this masked array from NumPy, which was mentioned in an earlier tutorial also, which allows me to take an array and replace some of the values with a mask, so that when I plot it, those values don't show up at all, basically. And MA has a lot of different functions associated with it. Again, take a look at the NumPy documentation, or do MA question mark in a cell to get some information about it. But one function it has is this masked where function, which takes a condition, hmax less than 0.001, for example. So wherever the depth is less than 1 millimeter, I'm going to mask the array hmax. So this condition is something which sort of has the same dimension as the array, and it has the effect that everywhere in the hmax array where the depth is less than 1 millimeter of water, we're going to mask it out. So now we have a hmax version of the hmax array that's masked out where it's dry. And this other array, hmax onshore, is masking out where the topography is less than 0. So the topography file is positive on land and negative for the underwater bathymetry. And so by masking it out where the topography is less than 0, I'm suppressing the data everywhere out in the water and only looking at the data onshore. And then I'm doing pretty much the same thing I did before, but now I'm going to plot this hmax onshore in this case. So I won't be, and the hmax onshore, by the way, started with hmax dry as masking it out. So it's both masked out where there's no water at all and also where there was originally water. So it's only the part that was originally dry land that got wet that's in this hmax onshore now. So when we plot it this way, what we see is the dry land up here in the high regions has been masked out. The original water has been masked out, and we can see more clearly what areas of the community of Crescent City actually flooded. Is that clear? And then we might not like this particular default color map very much. We might want something that's a little more illustrative of what regions have the most flooding, what regions the least flooding, so we might want to set our own color map, and I won't go through this in detail, but for this contour F routine, since it's filled contour lines, it's sort of solid colors in between different contour levels, there's a little function here that just sets one particular discrete color map in the form that's needed for this, which I'll let you go through on your own. But basically, what it gives you is an array of RGB values that will be used for each of the contour levels. So I've set the contour levels from 0.5 meters, 1 meter, up to 4 meters. And so between each of these contour levels, there's one row of this array tells you what the RGB value should be for that particular range of data. And then because our data might actually go above 4 meters somewhere, and we don't want it to just show up as white, we want it to sort of use the maximum color, which is red in this case. There's an argument extend equals max in the contour F command, so that anything that's outside of this range, that's above the range, gets the color of the highest level rather than being white, which it would be by default. So if we apply all of that, then we get a map that looks like this. So now we can see more clearly that right along the shore we have the deepest water going up perhaps above 4 meters, and in fact I put in a title command here that actually prints out what the maximum depth was, so we can see that, oh yeah, it was almost 6 meters in some places, but in order to make a more easily visible map of the differences, I've kind of limited the color bar to go up to 4 meters, but then the extend equals max gives you this arrow at the top which says anything that's red might be above 4 meters. And then here we've plotted this color map on top of contour lines, which might be fine for some purposes, but we might also want to plot it on top of a map or on top of a satellite imagery. There are various ways to do that. One thing that we're doing in our visualization project this week is to try to come up with better ways of doing that sort of thing. And I think tomorrow our group will show some of the results of what we've been coming up with. But one simple thing to do, if you have an image, and here I've got an image which is in this repository, which was just gotten by taking a screenshot from Google Earth, a very primitive way of sort of capturing an image, but that created a PNG file. But any image that you have, you could use as a background, and I've specified what the extent of that image is, and then using the Matplotlib function IAmShow, you can make a plot that simply has that image. So this is a satellite view of Crescent City. And then what we'd like to do is take that as our background and plot our data on top of it. And so the next cell does that. So basically, I've repeated that IAmShow command. And then I've also fixed it up here. It doesn't look quite like it has the right aspect ratio again. It's too wide. But we can again fix that with the set aspect command. And then I've done the contour F plot on top of that image with a transparency alpha equals 0.4, so that we can sort of see the image through the plot of the maximum depth. So that gives us a plot like this, where we can see the same contour F plot we had before, but now on top of this imagery with some transparency. And then there's a whole bunch of other commands in Matplotlib for doing other kinds of plots. Contour F is kind of nice for some purposes, and it typically plots very quickly, even for large data sets. But you can also do p-color plots, if you're familiar with those from MATLAB, which is just a pseudo color plot where it sort of interpolates between colors rather than giving these sharp boundaries between different colors. IAmShow can also be used to plot data in some cases if you have it on a regular grid. And I've put in some links here to some references on how to make color maps and choose good color maps and so on. So I won't say too much about these next couple examples, but this is a p-color map of the topography, so you can see now it's sort of a continuously graded colors instead of a discrete set of levels. And the next example shows sort of a relief plotting that you can do as well. And then finally, one thing we've been trying to do in the project this week is make better tools for dealing with these maps interactively. But one simple thing you can do, I'll illustrate here, to plot this sort of data on top of an interactive map is to use Folium, where we can specify a map center and a zoom level, and it pulls up this OpenStreetMap view using Leaflet, which is interactive, so you can zoom in on it. And so you might like to take this data that we have of inundation and plot it on top of this, and it turns out that's relatively easy to do too. So here I've taken the same data, turns out I had to flip the array in order to get it to come out right. That's one of the things that you're always sort of fighting with in dealing with Matplotlib in particular, and some of the geo data is making sure your arrays are dimensioned the way they're expected to, so they come out right side up and so on. But then what I've done is to use IAmShow to plot this data, but before plotting the data, I've applied a color map to it. So this is another way you can sort of specify a color map. You can normalize the data so the values go between 0 and 1, and then apply some color map to that data. Here I've just used one of the standard Matplotlib color maps from the CM color map module, which is reds going from white to red. But again, you could use your own color map if you wanted to use something fancier here. And so this gives a way of plotting that data just as an image. And then once you can do that, you can add that image to a Folium map using this image overlay function. So from Folium, you import the plugins module, and then this image overlay takes as an argument this colored data that we produced and adds it to the map M that we created up above. And then I'm displaying the map M again. And so that gives us a view of Crescent City where we have this map, this inundation data plotted on top of it, and we can interact with it. Okay, so I went through that very quickly, but hopefully that gave you sort of a basis to work through this notebook in more detail if you're not familiar with some of this and figure out these commands. Again, there's lots of documentation online, and you can access a lot of it right through the notebook. So I encourage you to just play around with things. We're going to switch off now, and Tony's going to talk about projections a bit, and then I'll come back and talk some more. But are there any quick questions while Tony's setting up? Yeah. I'm not sure offhand. Maybe Tony.
To the resolution of the map or the resolution of the overlay? Overlay. So that has to do with the resolution in which the data was simulated. So if Randy goes and runs his simulation at a higher resolution.
Right. If you're talking about the resolution down here, the pixelated values of the depth, that's because, remember, we only had like a 175 by 240 grid or something of simulation data. So it was on a resolution of about 1 arc second, which is about 30 meter resolution. So if I'd run the simulation more finely, or if I'd done some interpolation rather than just plotting cell values, then you might get something smoother.
Any other questions? Okay.